Allumage moteur Vulcain. Allumage confirmé.
Allo?
Dočuvane.
Salut. Servus.
Pronto? 여보세요? Allo? Hola.
Sawadee.
Welcome to the Exploratorium. I'm Senior Staff Scientist Paul Doherty, and I'm here to guide you through the latest happenings on the Rosetta mission. Rosetta is this spacecraft that's going to be the first spacecraft to rendezvous with a comet and accompany it as it goes around the sun. And it's going to orbit the comet as it does that, and it's even going to send down a lander to land on the comet. And it's loaded with scientific experiments to tell us the nature of this comet, the history of the comet. We're going to learn a lot from this mission. Now, we need to find the comet in order to rendezvous with it. And so here's, after hibernating around the orbit of Jupiter, they turned on the spacecraft again, and it got this early picture. That little dot there in that box is one of the first images of the comet taken by the Rosetta spacecraft. In this image, it's 1 pixel. It just fills 1 pixel. And this comet itself, we have Hubble pictures of it. It's about 4 kilometers in diameter, 3 miles or so. Here's the latest picture that they released from the European Space Agency. Rosetta has turned on. It actually is now, you can see that it has a little dust and gas coming out of it. It is a live comet, and that's where the spacecraft is heading. Well, in fact, today, right now, in fact, is the day of the big burn, the first big burn. The spacecraft is 1 million kilometers still from the comet, and it's approaching it at 750 meters a second. I'll translate that into English units. That's 1,500 miles an hour. And this burn is going to slow down the spacecraft by about 290, about 300 meters a second. It'll slow it down by 600 miles an hour. After the 8-hour burn, which is going on right now, I believe, the spacecraft will still be approaching the comet at 900 miles an hour. But it's got 500,000 miles to go. So having a little speed here is pretty good. So they're firing 4 thrusters right now to slow it down. Here's a picture of the spacecraft with the 4 thrusters circled. And they're going to fire those for 8 hours, and each thruster is called a 10-Newton thruster. And 10 newtons is actually the force of gravity on this 1-liter bottle. So 1 liter is about 1 kilogram. 1 kilogram is about 2.2 pounds. And each of those thrusters, if you hold this in your hand, that's the force of one of these 4 thrusters on this spacecraft. And I'm going to actually step forward just a minute and pass this around so the audience can feel 10 newtons. And there's an actual picture of the engine. This rocket motor, it's out there in the vacuum of space. It had better fire or this mission's dead. And it uses some really nasty chemicals. It uses hydrazine and nitrogen trioxide. These are nasty things. These are so nasty that if they touch each other, they burst into flame. I mean, there's no igniter needed. You just squirt these 2 chemicals in and they turn into a rocket thrust just by touching each other. This is a very reliable thruster, and we'll learn later, I think tomorrow, how well this burn went. And just to give you a picture of what's going on, this is a picture of my minivan. I have a Toyota Sienna minivan. It weighs exactly the same as this spacecraft. It weighs about 3 tons. And we're pushing on it with the force that you feel from that bottle. We're going to push in it, and it's going 1,500 miles an hour. And your job is to stop it. It's going 1,500 miles an hour relative to the comet, that is. And your job is to stop it by pushing on it gently for a long time. So that's what we're doing right now. That's the status of the mission. And it's really kind of interesting. So with that in mind, we have a special guest today. And that special guest is Dr. Claudia Alexander. And she's project scientist at Jet Propulsion Laboratory. Yay, Claudia! Yay. And that's one of my favorite places on Earth, and that's saying a lot, because Jet Propulsion Laboratory works, it's part of Caltech.
That's correct.
And I went to MIT. So we're a little competitive here, but they really do amazing space missions. So Claudia, start off by telling the audience your background. How do you get to be project scientist on a mission like this?
You know, I always wanted to do that. I went to Berkeley, and my choices were, you know, geophysics, which was they did earthquake geophysics,
Yeah.
and I was kind of more interested in the planets, and there was no direct path, and there still isn't. There's no such thing as a major in planetary science. But I went down and did an internship over at Ames Research, which is, you know, down the bay over at Moffett Field, and I learned about the planets by the little group that's over there. We were studying. I worked for the guys who discovered the volcanic nature of Io, Jupiter's moon Io. I worked for Pat Casson and Ray Reynolds, and those guys won a NASA medal for that prediction. So it was just, for me, I don't know, 18, and I was just fascinated that you could win a medal for a discovery like that, right? That was, in fact, I remember back in those days that some Japanese interviewer asked them, why would you even make this prediction when in 2 weeks the spacecraft was going to fly, and if you were wrong, you would just have been so embarrassed, and all you had to do was wait. So I mean, I learned a lot at the feet of these brilliant guys about what it means to explore space, what it means to make these predictions, and what the icy satellites, that outer solar system, how important it was to get to the outer solar system and to study Jupiter, Saturn, and understanding more about the outer reaches of the solar system.
That's fantastic. Actually, one of my students I had a grad student, and he did the calculations of the trajectory of the ejecta from the Io volcanoes back in the late 1970s.
Yeah.
So that's a fun. The equations are complicated.
I mean, to a certain extent, we're still dealing with that on Rosetta because you've got something that's spewing things out, and you're hoping that some of that stuff goes into the aperture, you know, of your instrument. So, you know, you're trying to figure out how do we catch some of that stuff in our mouth so that we can actually analyze it. So that's part of what we're trying to do even now, is understand what happens to some of that ejecta when it comes out.
So I think Jet Propulsion Laboratory actually has an instrument that has a mouth on it that sort of takes in maybe ions and electrons. What about that?
Okay, so let me just be clear that I'm the project scientist for NASA's contribution to this mission.
Yes.
This is an international mission. Yeah. It's led by the European Space Agency, and NASA only has about a 10% participation in this international mission. So it's kind of like the Cassini mission, which was a NASA-led exploration of Saturn, where they dropped a probe into the atmosphere of Saturn, and that probe was a European probe. It's kind of the opposite. Now, Europeans are going to explore a comet, drop a lander, and NASA's contribution is about 10%. And the instrument that you're talking about is produced by Southwest Research Institute in San Antonio, Texas. So it's actually kind of a knockoff of the Cassini CAPS instrument. It's the same institution and a lot of the same investigators, and we put that instrument on Rosetta. And JPL's instrument is a microwave instrument, so it doesn't have an aperture.
Oh.
It's what we call remote sensing, which kind of is like what happens in a department store when the security guard is sitting at the desk, watching what happens around the store using cameras. That's remotely sensing what's going on in some place where you are not.
Yeah.
And an in situ instrument with an aperture, stuff actually has to go in.
Right.
In order for you to be able to tell what's going on there.
But they have some of those, it's just not your instrument.
That's not ours.
Okay. Well, that's good. So there's this comet out there, and this is our first chance to actually be with a comet for a whole year as it falls around the sun. Right. What are you most looking forward to learning about this comet? What's the big payoff from being there in place?
I've got so many questions myself. Okay, one of is what makes this thing dark?
Yeah.
You may, I don't know, in your life have heard comets referred to as dirty snowballs.
Right.
And you may remember the wonderful picture from the 50s of Professor Whipple. He must have gone outside and built some sort of giant snowball, right? Because they literally had it on his desk in the university, and it, had dirt in it,
Yep.
and he said, this is a comet. This is what a comet is. And we had that in our heads for quite a long time, but now we know that they are black objects. They are not bright and white like a snowball. They are dark. Well, we used to say they were dark as asphalt.
Yeah.
And one of my colleagues went outside and measured the asphalt in the parking lot, and it's not really that dark, but
Right.
they're really, really, really dark objects in space. And so one of my questions is, what is it about the material that makes it dark? We used to think that it was covered with a shell, a crust. And it may be that dark stuff all the way through. So I want to
Wow.
get a chunk of that stuff up into the atmosphere
Yeah.
and try to figure out what it's made of.
Taste it, smell it.
That's right. Right.
Mass spectrometer it.
That's right.
Yeah, we'll see. Aromatic hydrocarbons or whatever it's going to turn out to be.
Where it turns out to be.
Yeah. In fact, I have a picture. I don't know if we can switch over to the picture of a bunch of Harvard students rolling looks like an 8-foot diameter snowball. There it is. And from the size of the comet, I guess it's like 3 kilometers by 5 kilometers, sort of.
It's the size of Central Park.
Ah, that's pretty cool. That's a good size. I didn't have that number. And from its mass, which is like 3 billion tons, we can work out the density approximation. But of course, those numbers are really plus or minus, and it comes out to about the density of a snowball, I think. So that's pretty good.
So in most respects, and when you look at the spectra from the ground using your remote sensing capabilities, it looks a lot like water. And so you're just going, okay, a snowball, that makes a lot of sense. But then when you actually see it, what we know about it, it really doesn't behave like it. It doesn't look like it, even though it has that density of like a snowball.
Right.
If it's made of that dark stuff all the way through, that really raises some questions. Maybe it's stardust.
Yeah. Yeah, where did this... So, in fact, before we started, one of the audience members came up and asked me, so how was this comet made? And I sort of answered, well, that's what we're trying to find out. But is that what we're trying to find out?
That's what we're trying to find out, okay? Yeah. And the tricky thing is that it's very difficult. I was just talking yesterday with someone trying to explain, it's like going to a crime scene. And you're trying to get the forensic evidence that's going to help you figure out the crime, right? And you want to pinpoint the defendant at the place of the crime, using all these fibers and using, isotopic evidence. And we're trying to do a birth scene. And our ideas about what happened at the birth are very confusing. It's very difficult to sort out, and not a lot of things make sense. And so part of what we're doing is like a detective, we're trying to gather the evidence. We're not ready to go to trial yet with our case. We're still trying to gather the evidence about what happened at the dawn of the solar system. Yeah. And let me say this, which is that most of the things we have, pieces of evidence we've had up until now are meteorites, which is stuff that falls on the ground. And you're picking up stuff that fell out of the sky, and you're trying to use that stuff to figure out the dawn of the solar system, and you don't have enough pieces of evidence.
Yeah.
So going to the comet is giving us a whole different sort of object from the solar system's beginning to help us fill out our understanding.
Yeah, and I actually understand that this Friday night in San Francisco area and Saturday morning, we have some of the dust from Comet Linear, which may make a meteor shower.
That's awesome.
So I'm heading out at midnight on Friday night to look at the sky, and it's, as any meteor shower is, it's a roll of the dice. You don't know how many you'll get, but those are bits of comet dust, the tail of the comet hitting the Earth's atmosphere.
Yeah, I mean, obviously, I'd be very surprised if any of that gets to the ground.
Yeah.
Being able to see it in the sky is really cool and great. But you know, up until now, the little hard bits that you pick up off the ground, a lot of those come from asteroid Vesta.
Ah, yes.
From one source in the first place.
Right.
So it's really a unique experience to be able to fly out to meet an object that was maybe there at the dawn of the solar system to help us, you know, to give us everything it can tell us about what was happening then.
That's going to be fantastic. And as you said, you have the suite of instruments, remote sensing. I guess you can look in many different wavelengths and identify the chemicals. They have the samplers that can separate out even the isotopes of different different atoms and molecules, sense the molecules, and find out really what this comet is made of. And I guess maybe the isotopes, like water, comes with oxygen of several different kinds, you know, oxygen 16, 17, 18, and that's a clue. It's one of these forensic clues you're talking about the birth of this comet.
Yeah. So I mean, so it sounds a little bit archaic, but the flavors of those isotopes, oxygen 16 and oxygen 18 and oxygen 17, if there was a supernova that went off, that will create different flavors. And so when we go and we're going to be looking at how these different isotopes relate to one another, and hopefully that'll help us try to sort out, did we have, some people are saying, well, it was a Wolf-Rayet star that went off and not a supernova. And all of those things are stuff we really hope to learn more about.
I just had the image of licking a snowball and saying, I think this is really rich in oxygen 17.
Yeah, exactly. Right. This doesn't taste like Earth water at all.
Yeah. I guess there are two main theories in planetary science about where does the Earth water come from.
Exactly.
Was it from volcanoes or was it from comets?
Now, a lot of people, there was the most recent Comet mission, one of the fellows on our team, a German guy, made this observation, and he says, we made this one measurement, and now we can say that comets may have brought the oceans to the Earth.
Yeah.
There's a lot of people who believe that, and there's a lot of excitement, and people want to go, and they want to, show that Earth got its oceans from comets, and certainly there's enough volume of comets to do that. But I'm sort of the group of people that believes that Earth is perfectly capable of bringing forth its own oceans. And I'll tell you, this may sound silly, but I was making butter in my kitchen a few months ago, and when you're making butter, you beat it. It becomes whipped cream, you beat it some more and it starts to get solid, but you have to keep beating it, and then there's a moment when what looks like butter begins to expel all of its water. And then the water becomes buttermilk, you can make pancakes and stuff.
Yeah.
And then what's left behind is the butter, and I feel like in geochemistry, hydrated minerals like we have on the Earth are capable of, under pressure, expelling their water, and I think that's equally good explanation for where Earth's oceans come from.
I'm on the fence with you. I started out in physics and planetary physics myself, and I believe perfectly in the capability of rocks when melted to release the water of hydration.
Yeah,
but it's a great question, and data is going to answer it. And this mission will really help us get maybe a second data point. In science we always say, great claims require great evidence. And so if you're going to claim where all the water on Earth came from, maybe you'd have like 3 different experiments to confirm it.
More than one measurement.
That's it.
Exactly.
So we're talking right now with Dr. Claudia Alexander, who's project scientist at Jet Propulsion Lab working with NASA on the Rosetta mission. And she is a planetary physicist, and she's been involved with many different missions and really knows the different missions, the ones to Jupiter and Saturn, and now to a comet. So it's really wonderful to have staff scientists. Now, I had a different sort of question, which is, so you have quite a broad background, I think, in planetary science, looking at your background. And so here you are, a project scientist, managing a group of cats. I mean, you have all of these experts in the world's expert in the tiniest little fraction, one instrument. And how is it to manage a bunch of scientists like that?
Very interesting.
Yeah.
Yeah, I mean, it is. It takes a special temperament to be able to work with groups of experts.
Right.
Each one of them has more expertise than you.
Yeah, right.
It's, as you said, it's a project scientist has the breadth and is able to understand all of all of the different disciplines. But a lot of the people have a lot more depth on any particular one, and a lot of people they want to be the world's leading expert. And they want to be the one who's on TV, and they also want their particular measurement is more important than the other guy. And so right now, our biggest problem in trying to decide where we go with Rosetta, this is like flying near that, there was that Icelandic volcano.
Yeah.
That every time it would erupt, every plane, if you were flying from New York to Paris or something, they would be like, no, you're grounded. We can't go anywhere for days until this volcano stops erupting. Because planes don't want to fly through the dust, because that kills your ability to stay aloft.
Yeah.
And we kind of have that situation with Rosetta, because it'll be putting out these jets, it'll have a lot of dust, and we want to, on the one hand, there's some experts who want to fly through it. That's why we built the spacecraft. That's why we're there. We're going to fly through that stuff. And other scientists are like, we don't want to touch it. I'm telling you, I'm not going in there. So, it really is a fun challenge to try to pick out and make decisions about how we're going to achieve what we set out to achieve and keep everybody reasonably happy.
Yeah, keep the spacecraft alive in order to take the data.
Yeah.
And I suspect maybe, you'll have to watch the jets develop and measure the density and the particulate size so that you know how close you can approach this dragon.
The problem is here that we won't have time. It's kind of like you have to predict the weather, but we don't have time to build the models that will allow us to do that prediction before you want to fly.
Right.
That is a really huge problem that we're dealing with right now.
Right. So you're learning as you go.
As we go. We're learning as we go. The engineers are learning to fly as we go, because nobody's ever done this before.
Yeah.
We're making changes to the trajectory on the fly. I have never been on a project where we were able to pick what trajectory we wanted.
Right.
Okay, next week we want to go, here, and to make those changes to adjust so quickly, that is completely different, and it's going to be an incredible challenge, a really fun challenge.
Well, I'm looking forward to the results of this mission, and I'll be thinking of you when I finally see the data. I'm sure that when I go to the American Geophysical Union meeting in San Francisco this December,
you'll see me.
I'll see you there. I'll look for you,
Okay.
and we'll bring our camera along and continue this interview then.
Okay,
and
yeah.
so I'd like to
have our first exciting results we hope to have by that meeting.
Right.
The lander is on November 11th.
Right.
By 30 days later, we hope to, at that session that you're talking about,
Right.
hope to be able to present our very first results from the landing. So we're very excited about that.
I'll be there bringing it to our audience, and look forward to seeing you there. Dr. Claudia Alexander from JPL. And we actually, before she goes, does anyone, should I do a question from the audience? Is there any questions in the audience while we have an expert here? We have one over here in the corner. Ron. Okay, good.
Claudia, you mentioned that most of the meteorites that we find on the ground are from Vesta, and that includes all the forms of meteorites, the chondrites, the nickel irons, the pallasites, they're all from Vesta?
No.
No. Which ones are from Vesta?
The chondrites, but not all the chondrites. What I'm saying is that Mars and Vesta are the two most common original sources of what we are able to pick up off of the ground.
Yeah.
There's other sources, but the most common source seems to be Mars and Vesta.
Oh, great. Another question? Yeah. Oh, here we go.
Hi, Claudia. Thank you very much. What's your best guess and or the best guess of your team about where comets really come from?
There's really two homes of the comets. One is the Oort Cloud, which is completely surrounds the solar system and is at enormous distances away, 300,000 AU, an enormous distance. And those Oort Cloud comets come to us kind of out of the blue. Literally, they take us by surprise. Now, the other comet home is the Kuiper Belt, what's called the Kuiper Belt, which is beyond Pluto. And those comets kind of cycle in, they get disturbed, they come in. Jupiter collects a lot of them, so there's kind of a swarm of comets around Jupiter, and eventually some of those get knocked into the inner solar system, and they're called short family comets, and those are the ones that NASA gets to visit because those are the easy ones to actually plan for and target. So we know kind of where they're coming from. The question is, how did they get there? You know, I mean, the idea is that, okay, so there's one set of theories called the Nice model, because a bunch of people got together in Nice, France, and this is the only thing they could agree on, was that somewhere along the line, the comets in the Kuiper Belt and the Oort Cloud were between Jupiter and Uranus, and Jupiter and Saturn and Uranus and Neptune were oscillating like mad, and then Uranus and Neptune changed places. And in that event, kind of like a billiard ball, when you set the billiard table and you said all the debris went flying everywhere, including into the inner solar system in what might be the source of what they call the late heavy bombardment.
Yeah.
So that's just one idea of where the comets came from. And so part of what we're doing with the forensic evidence is to try to get the isotopic signatures that help us to pinpoint where and when, not only where in place, but when in time the material came together to form our comet that we're studying.
Yeah, I actually have
question.
I have an image here of the Oort Cloud and the Kuiper Belt. I don't know if we can switch to that. There we go. So you can see the little blue circle there is Pluto's orbit, and outside of that is this sort of disk, which is the Kuiper Belt. And then in the bigger image, that little tiny blue disk in the middle of that bigger image there, it shows the Kuiper Belt again with the Oort Cloud around it. And this Oort Cloud goes a good fraction of the way to the nearest star. I mean, that's where the comets come from. So it's quite an amazing thing we'll be looking at here. So I think maybe there was another question. Did Alex have a question? Oh, right there. Okay, one other question.
You may have already answered this and I didn't hear it, but how long does it take a signal to get to there? Is it like a near real time that we can actually operate on this robot?
It will change as the comet comes into the sun. It will be about I think 1.4 AU when we go to perihelion. So that'll be just a few minutes, a one-way light time. But right now, and the closer it is to Jupiter, it's more like 45 minutes.
Yeah. Any, okay, so I think that's all of our questions. So thank you, Dr. Alexander. That was really great. And it's nice to see you able to smile at this point in the mission where the big burn's going on. So we look forward to having a successful burn and a good orbital adjustment and getting closer to the comet and answering some of our pressing questions.
Great.
So let's give a thanks to Claudia. And thank you very much.
All right, then. Bye-bye.
Bye. Okay, so here we are back in the Exploratorium. So I'm going to sign off, but I'll stay on if you have other questions about this mission. So I'd like to thank our audience for coming and being here as we did. That's our first live connection in the webcast theater to another place, and it actually worked. If only the mission works as well, we'll be in great shape. So, yay team in the back. So, whew.